We'll start today by having you meet the other members of our instructional staff, the folks who you'll be seeing on a regular basis each Tuesday in your respective discussion class gathering. When you go for out-of-class help in the Chemistry Learning Center, you want to see these folks, because these folks will be in the know. Myself or these folks. We're missing one person, that's Mackenzie Coughlin, but she has a class, so may not have been able to attend today. But you'll get to meet her in the future nevertheless. So, in a loud and clear fashion, introduce yourselves individually to these people. Go ahead.
Hi, you guys. My name is Ling, and nice to meet you.
My name is Tu Nguyen. I'm a graduate student. He's my keyboard student.
Yeah, this is my master. I'm a protege. My name is Hunter Clutch.
You may be seated. We have our remaining instructional staff member with us right now. Others have been introduced. Now it's your turn. Don't look at me, look at them.
Hi, I'm Kenzie. I'm currently the TA for fourth period on Tuesdays. What else do you want me to say?
Nothing else, that's it. Just wanted them to get to know you.
Okay.
Thank you. She's got a class, she's got to run off to it. Some of the folks you just saw were people who sat in your seats one or more semesters ago, who put up with this gathering. Put up with it quite successfully, I might add. Successfully to the point that when they approached me and asked for the opportunity to teach a discussion class, I said, wonderful. Why? Not only did these people succeed in demonstrating that they have the ability to wrestle with this material, but by requesting the opportunity to conduct a discussion class, they indicated that they want to be able to have the opportunity to participate in the educational process and assist you folks in getting on with this stuff, because this is important stuff and it's difficult and challenging stuff. So I'm very happy to have had these folks step forward and on a volunteer basis become members of the instructional staff for this class. The graduate students involved have also done this class before, and have also proved themselves to be wonderful at this stuff. That's good. It just helps us have the better opportunity to get on successfully. So with that, if you are here today for the first time and haven't got the syllabus for this lecture class or the corresponding lab, come get it right now. Anybody in that category? If you don't have it, come get it right now. You got to have this stuff. And I trust the rest of you now have chem notes. You folks, if you haven't got the chem notes, you will need to have that note package immediately.
In the bookstore?
Any of the local bookstores. This is the text for the course. But I have to hold up my note package carefully because, as you can see, it's well stuffed with notes that I've written to myself regarding the notes that are contained within. One thing I forgot to ask you last time. Who can translate this? CPO exclam. What does that mean? Tell me. What does it mean? It means cell phones off. My expectations are that most, if not all of you, are armed with these devices. I never had one and swore to never get one until about 4 years ago I became romantically involved with a wonderful person who is now my beautiful wife. She commanded me to get one. I said, yes, dear. But I try to remember to leave my cell phone in the office. Just be sure, please, that the damn thing is turned off. Because if the cell phone, your cell phone, makes its presence felt during our gathering by playing whatever interesting ring pattern you have set to it. I have a special cell phone deactivation device in the back room. It's called a sledgehammer. It works well. I've never had to apply this device to any ringing cell phone more than once. After which that cell phone has never made another sound again. CPO, cell phones off. Now, to pick up from our point of departure. We finished last time by shoveling a rather large scoopful of calcium chloride into about 400 milliliters of deionized water, and found out that after a little bit of stirring, shaking, all the calcium chloride dissolved. We took about a similar sized quantity of calcium carbonate, a few grams, shook it into the same quantity of deionized water, 400 milliliters, and found out that on shaking vigorously, all the calcium carbonate did not dissolve. Here we have that system, except now you'll see the calcium carbonate, because it's more dense than the solution portion of this system, is settled to the bottom. Can you see the white stuff at the bottom? That's the undissolved calcium carbonate. In which of these systems does equilibrium exist? Equilibrium between solute and solution. Let's comment both. system?
I was going to say the same.
Both.
Both?
The calcium carbonate.
We got 2 votes for the both and 2 votes for only the calcium carbonate. Obviously, these sets of votes cannot be each correct.
I was going to say the calcium chloride.
Calcium chloride is equilibrium. How we got calcium chloride? 3 votes for calcium chloride. The calcium chloride system, where all the calcium chloride dissolved, is ahead in the vote count.
Calcium chloride?
4 votes for calcium chloride.
I'll second or fifth that.
5th vote for calcium chloride. Let's stop the votes because we're traveling in the wrong direction. I'm going to write a statement on the board. Well, I'll ask you to write this statement on the board. When we prepared the calcium chloride solution, write the equation for the reaction which occurred on dissolving the solute. Write that on your paper right now. The equation for the reaction occurring when we dissolve the calcium chloride. Then later we'll talk about writing the equation for the reaction on saturating water with calcium carbonate. How many wrote this? If you didn't write this, what you wrote is not correct. When an ionic compound dissolves in water, at the minimum, the ionic compound always separates into its component ions. This separation process has a name, it's called dissociation. That's why I wrote dissociation after this statement. Now then, in order for equilibrium to exist, we must have a reaction system where the rate of the reaction in the forward direction and the rate of the reaction in the reverse direction are identical. Remember that? Here's the dissolved calcium chloride system. Is there any residual calcium chloride? Well then, if there's no residual calcium chloride, how could this reaction system be in equilibrium? There's no more of this. How could it continue to go that way if there's no more of this? Is this equilibrium? No. But is this one equilibrium where we dissolved the calcium carbonate, where we did not, however, dissolve all the calcium carbonate? Is equilibrium? Yes. Because in order for equilibrium to exist, in order for these rates, reverse forward, to be equal, there must be in the system measurable amounts of both reactants and products. If for the reaction system you've studied all the reactants go away, no equilibrium, at least not involving reactants. No equilibrium involving solute. All right? Now let's pause for a moment before we proceed. Because we started with this system with just deionized water. So I'm going to do that again. Calcium chloride is a safe stuff, so I can remove the calcium chloride solution by disposal into the sink and recharge our flask with deionized water only. Now these Erlenmeyer flasks, that's the name for these conically shaped flasks, They have approximate volumes printed on the side, but these volumes are not very accurate at all. If you wanted, in a reasonably reliable fashion, to evaluate the equilibrium constant for the equilibrium reaction which lives in this flask, how would you do it? Now, to try to be sure you understand my question, let's draw a picture of this flask over here. Contents deionized water only. And as we discussed last time, in this stoppered flask, this equilibrium system exists because the water vapor produced by evaporation of the water liquid can't escape. Secondly, which we'll talk about in greater detail, in writing an equilibrium constant, which is a quantitative relationship for the equilibrium system in question. In writing this equilibrium constant expression, symbolized by capital K, don't get K confused with K for Kelvin temperature. In writing the equilibrium constant expression for any system, the components of the equilibrium system which are included in the equilibrium expression are the dissolved solute species and any gases which are part and parcel of that system. Everything I'm telling you is in the notes. So if you read the notes, you will certainly see in writing what I've just told you. Solute species, gases. That's it. So right above this, K contains solute species, expressed as this. What's this? Square bracket notation for concentration. What kind of concentration? Molar concentration. What's the definition of molar concentration? Don't tell me moles per liter, because I won't accept that. I want a more specific definition.
Moles of solute over liters of solvent.
Nope, that's close. Moles of solute per liter of solution. That's correct. Square bracket notation for molar concentration. Alphabetically symbolized by italicized capital M. That means molar concentration. So, the equilibrium constant expression will contain solute species expressed as M and or gases. Expressed as, or in terms of their molar concentrations, or better yet, this. Chemists, from a thermodynamic standpoint, prefer to express gases, which are part of an equilibrium system, in the equilibrium constant expression in terms of, what is that? Partial pressure. All right? Now, let's put this K up here. Now let's go back to our flask. Here's the equilibrium which lives in this flask. What is the equilibrium constant expression for this equilibrium? It can be written two ways. It can be written as this. Do we include molar concentration of water in this expression? Water liquid? No, because that's the solvent portion of this system. Its concentration is constant. Liquid water. Doesn't make any difference what size amount of liquid water we have. The concentration of water in pure water is constant. Pure water, liquid. Or, better yet, we'll write K sub C, because this is an equilibrium constant expression expressed as a concentration, molar concentration. Maybe we could use the symbol K sub M for molar concentration. But chemists do it this way, so I'll use this. The preferred way to express this equilibrium constant for this equilibrium system is this, in terms of the partial pressure of water vapor. Okay? One more aspect of writing an equilibrium constant, and you'll see this as we write equilibrium constants for the reaction system we're going to look at today, is that by convention, in the equilibrium constant expression, molar concentrations and or partial pressures for products in the numerator. Consequently, molar concentrations and or partial pressures for reactants in the denominator. You probably know this already. The last part is, for the equilibrium reaction equation, if you see coefficients which are other than 1, then you will take that molar concentration for that species and raise it to that power, the power corresponding to the coefficient for that stuff in the equation for the reaction. Same for partial pressures for gases. Okay? Saying all this stuff is kind of clumsy. But after you write a couple of equilibrium constant expressions, you'll know just what's going on. So let's go back to this system. After having recognized that the equilibrium which exists in this system is this and can be expressed as a function of molar concentration of water in the vapor phase or the partial pressure of water in the vapor phase. If you were in laboratory and you prepared this system, very difficult job. You take a flask, put some deionized water in it, stopper it, and give it a couple of shakes, and there you have it. How would you evaluate this? How would you get the molar concentration of water vapor?
First, don't you need to measure the pressure, and then you can find...
Oh, I want specifically what you're going to do. Okay. If you tell me measure the pressure of what?
Of the open air system. Of the open air. In the system.
The open air, let's imagine, is 760 torr. Well, in Florida, it's usually about a nice sunny day like this. I'll bet atmospheric pressure today is 765 torr. Usually a few torr above normal atmospheric pressure, which is 760 torr or 1 atmosphere. Then what? I'm giving you that.
You can use the ideal gas law to find N from that.
Ideal gas law?
Yes.
To find N from that?
Yes.
How are you going to use the ideal gas law if you don't know V?
That is true.
That is true.
You need to measure that first.
I want to know how we're going to measure V. Here it is. This is the V occupied by the gas. That's not the same as V in the entire system. This is the V you're concerned about. Here's the flask. How in the laboratory would you determine this V?
You turn it upside down
All right?
and measure it from that way.
You can?
Not really.
Never mind these graduations, because the flask I give you in lab won't have any markings on it. All right, I want you to think about this. And we'll talk further about this system later. Are you understanding the problem?
Well, I have an idea.
Well, keep your idea on hold. Okay? We want to be sure all of you can wrestle with something like this in a sharp and clear fashion from an experimental standpoint. Again, imagine you're in the lab. You take a flask with no volume markings on the flask. You partially fill the flask with deionized water, you stopper it, you shake it, so as to establish the presence of that equilibrium system within the flask. You then have the job of evaluating K for that system in terms of molar concentration of water vapor or partial pressure of water vapor. That's your task. And if you learn what you're supposed to have learned in 2045, you know how to do this. And if you didn't learn what you were supposed to have learned in 2045, you probably don't know how to do this. We're going to find out. I argue often with my 2045 lecture colleagues that you do not invite these students in 2045, as it is presently taught, to think. This problem involves thought. And I don't like that. But I better not go too far in starting a fracas with my 2045 lecture colleagues. But for those aspects of 2045, like this, which require thought, we're going to talk about them frequently. And we'll always supply the information that you need to have to wrestle with the problem. If you didn't get it from 2045, you're going to get it here. Okay? But for now, we'll postpone the answer so that I can invite you to refresh your memory on stuff from 2045 that you wrestle with to see if you can answer this. I'll give you one clue. To evaluate one or both of these equilibrium constants, beside measuring volumes, what other measurement do you have to make? Beside measuring volumes. Yes! You got to measure this too. Keep that on hold. All right, let's proceed. For system small Roman 1, the calcium chloride system. If we dissolve sufficient calcium chloride to make 1 molar calcium chloride, and after having done so, recognize that all the calcium chloride is dissolved, clearly it must have, if we dissolved enough calcium chloride to give us a concentration of 1 mole calcium ion and 2 moles chloride ion per liter of solution, we can't have equilibrium here because all the solute calcium chloride disappeared by dissolving. We saw it. All right? Now then, no EQ for I because all solute dissolved. I repeat, for equilibrium to exist involving solute, after the reaction which involves solute on dissolving the solute takes place, if that goes to completion, no equilibrium because all the dissolved stuff disappeared. Let's look at system 2. We'll not pursue system 2 by demonstration, because there really wouldn't be anything to see. Hydrogen chloride is a colorless gas, and water, as you certainly know, is a colorless liquid. What's the equation for the reaction that occurs when we prepare 1 molar HCl? Write that on your paper right now. The equation for the reaction that occurs when 1 molar hydrochloric acid solution is prepared. You did stuff like this in 45 laboratory, and I want you now to put it to use. How many wrote this? If you wrote anything but this, what you wrote is not correct.
Is it alright to write it the way we did number 1, with the solute on the arrow?
You mean to write water over the arrow? It's really not necessary because you see that this system involves water liquid. I mean, writing this up here is not necessary because once you see the AQ tag, you know water is the solvent. Okay? I purposely, for system 1, wrote water above the arrow to remind you that even though calcium chloride was dissolved in water, preparing calcium chloride solution involves no reaction with water. All the water did was to provide an insulating medium after separating the calcium ions and the chloride ions from each other to keep them apart from each other so as to prevent their recombination to remake this stuff. Water did not participate in this chemistry. It is the medium in which the chemistry occurred. But water is not a participant in this chemistry. So be careful, because students often think that when I prepare a reaction system by dissolving something in water, water must be part of the reaction. No, it may or may not. It clearly is part of the reaction in dissolving hydrogen chloride, because this reaction involves H plus transfer from the HCl molecule to the water molecule to produce hydronium ion, and after I strip H plus from HCl, chloride ion. This reaction has a name other than dissociation. This is a dissociation process because HCl molecules do dissociate. But a more specific name for this process is ionization. Why? Because this process creates ions. These are molecules. They have no charge. But after this reaction has taken place, we have ions. This reaction made ions. This reaction did not make ions because this stuff is ionic. What would you do to prove that calcium chloride is ionic? Another 2045 question.
Test like the conductivity of the solution.
What solution? You're going to test the conductivity of HCl solution to prove that HCl is molecular?
Well, because if it has a higher conductivity, then it's going to...
The HCl solution will have a higher conductivity than the calcium chloride solution if the total ion concentration for this system is adjusted so that it's equal to the total ion concentration for this system. Because you see, this thing puts 2 moles of chloride ion in the pot. If I make 2/3 molar calcium chloride solution, you'll find out that the HCl solution has a higher conductivity because this is the most conductive species in water solution. My point is, you cannot find out if a solute is ionic by testing the conductivity of its water solution. Because the solute may have reacted with water to create ions, like HCl. So the fact that HCl solution is quite conductive would hardly verify HCl being an ionic material. What you need to do
test the reactivity of its components and with a solid, like put it in an aqueous solution and test the reactivity with another metal?
No, too complicated. No, no, no.
How like if it has a metal and a non-metal?
Well, you're just looking at the formula. Did you learn in 2045 that a lot of compounds composed of metals and non-metals are molecular?
Metals and non-metals together are ionic.
Oh no. Many of them are quite covalent, quite molecular. We'll talk about that further in this class.
You could test to see if it would...
What's it?
you can test to see if the calcium chloride would dissolve in a non-polar covalent solvent.
Well, that'll give you some information. I want a specific investigation performed on calcium chloride itself to confirm that calcium chloride itself is ionic.
If you dissolve it in solution, then back.
Now, I don't want any solutions. I want an investigation performed on pure calcium chloride.
If you convert it to liquid and test chemically, then
We're going to melt calcium chloride and find out if the melt is a conductor. And we'll find out it's a marvelous conductor. Calcium chloride solid, even though it's ionic, is not a conductor at all because the ions are locked in the crystal lattice. They can't move. Did you learn in 2045 that a stream of ions is a current? Any stream of charged particles is a current. Doesn't have to be electrons. Any stream of charged particles is a current.
You could test a change in pH.
Change in pH? No change in pH in making calcium chloride solution. Remember, properties of an ionic compound. Did you learn about this in 2045? They're crystalline. They have high melting points or decomposition temperatures, one or the other. And a melt of an ionic compound is itself a good conductor. That's what you do to find out that calcium chloride's ionic. All right? Now, what would you do to find out that HCl is molecular? The information you need is on the board. If, under normal laboratory conditions, the conditions which are with us here in this room, you observe a pure substance to be gas, like HCl, could it possibly be ionic? Are there any ionic compounds which are anything but crystalline solids at NLC? No. Now, equilibrium. EQ in this system? The answer lies in the extent of this reaction for 1 molar HCl. Anybody know the extent of this reaction for 1 molar HCl? What's the extent? What's the extent? Almost. 100%. That's it. So now, I'm going to erase this and put in 1 molar HCl. We shall imagine now that our flask is containing 1 molar HCl, which by physical appearance would look just like our water. You've seen hydrochloric acid solution in laboratory. You've used hydrochloric acid solution in laboratory. You know its physical appearance, eyeball observation appearance, just like that of water. Colorless liquid with water being the solvent. I want you to tell me, here's the label on the bottle. This is the chemistry which occurs when the solution in this bottle is prepared. This will be our first attack on a consideration. which I hope some of you remember being introduced to in 2045 laboratory. How do you remember in 2045 laboratory being asked to think about principal species inventory? Point. If you're going to do chemistry on a system like this system, do you think it's possible to do that chemistry correctly if you don't know what's in the system? Second grader can answer that one. So I wonder why chemistry textbook authors can't answer this correctly. That's why I don't want those damn dumb general chemistry textbooks in this class. I don't allow them in this class because they're full of junk. Here's our first look at this full of junk contention. We've talked about what happens when this solution is prepared. On your paper right now, I want you to write the formulas for every principal species in this system. 1 molar HCl. What's in here? That's what an inventory is. If you work at Publix and the boss tells you to make an inventory, the boss is telling you to run around a store and make a list of everything you got. And if the boss wants the inventory quantified, then you have to write down how many. How many apples? How many Jonathan apples? How many Red Delicious apples? How many loaves of Publix white bread? Blech. I want the principal species inventory for this system. The answer to this directive follows directly from that chemistry which we've just talked about. If your eyeballs had super magnification power and were able to look into this solution, what would you see? What species would you see? Would you see this? Didn't this reaction go 100% when we made this solution? And isn't one of the products hydronium ion in aqueous phase? Yeah, you'd see that. Would you see this? You're damn right, because that's also a product of this reaction. What is the principal component of this system? What's the stuff you'd see most of the time when you looked around to look at what's in this system? Here's what you'd see. All right? Now, would you see any of these things? You wouldn't see one of these things. So how the hell can chemistry textbooks talk about HCl solution and write that damn fool stupid formula on the board? Because it's wrong. There's no such a thing as HCl-AQ unless you make this HCl solution about 8 molar or more concentrated. Because until you make it that concentrated, all the HCl molecules react by this process. The people who write these books would flat float this course. Martin Silberberg, he wrote the book you use for 2045, didn't he? He sat in my office one day for 1 hour. I'm serious about this. And listened to me rail at him about this junk. He said nothing, walked away quietly, and never did a thing about it. Kept writing that junk. And I told Martin, as long as your book contains that junk, your book will never appear in my classroom, period. It functions as the doorstop that we talked about on day 1. All right, we go to system 3. Now, The shorthand abbreviation for the acetic acid molecule is this. That's not a true chemical formula. About the best typed version for the formula for acetic acid that you can have is this. One molecule is composed of 1, 2, 3, 4 total hydrogen atoms, 2 oxygen atoms, and 2 carbon atoms. But for the acetic acid molecule, for which this is the best type formula, there are no oxygen to oxygen bonds. Sometimes writing formulas for material is difficult, because the most important property of any chemical species is what? Structure! We have to have structure known correctly if we're going to recognize how and why the stuff behaves as it does. And sometimes formulas belie structure like this. So if I give you this formula and I tell you there are no oxygen to oxygen bonds in the acetic acid molecule, which is true, I want you now to draw me a picture for the acetic acid molecule, specifically this picture. What's that? Lewis structure. You learned about Lewis structures in 2045, didn't you? Well, let's find out how well you learned about Lewis structures. On your paper right now, Lewis structure for the acetic acid molecule. Now take note, when I write Lewis structures, I try to write them in a fashion which corresponds to shape as well as I can. And when I write Lewis structures, if I can avoid such, I do not use dots for non-bonding electron pairs. I'm up here working with a smear of chalk all over the place. If I start using dots for non-bonding electrons, I won't know what the hell's a chalk dot or an electron dot. So I use sticks, because these are all paired electrons. They all represent electron pairs which live in the same orbital. So why the textbooks insist on using dots, I do not know. How many wrote this? Pretty good. What's the shape of this thing? What's the shape of this molecule in the vicinity of this carbon atom? Tetrahedral, because this carbon atom is how hybridized? sp3, and tetrahedral geometry is what you associate with sp3 hybridization. If, for the sp3 hybridized atoms, you have 4 peripheral atoms to it. 1, 2, 3, 4. What's the geometry of this molecule in the vicinity of this carbon atom? Trigonal planar, because this carbon is how hybridized? sp2. Good. So we're going to go back. This is our shorthand reference for this molecule, because this is a little bit clumsy to write. Pure acetic acid is, under normal laboratory conditions, a liquid stuff. But it can crystallize if you get the temperature around 20 centigrade. It's got a melting point around 23, 24 centigrade, something like that. Tell me, what do we do to this Lewis picture? To turn it into the Lewis picture, for this thing. Take the hydrogen off the oxygen. Take the hydrogen off the oxygen in what fashion? You see this OH bond here? Right here? Okay. I'm going to draw a picture. How many ways can I break this chemical bond? 3. That's correct. I can break it this way, which divides the electron pair in half and creates uncharged particles after the bond breaking process. Or I can break it this way, which breaks the bond so as to give this previously bonding electron pair to hydrogen. Or I can break the bond this way, which gives this bonding electron pair, after breaking the bond, to oxygen. 1, 2, 3. For this reaction, how did I break this bond? 1, 2, or 3? 3. That's correct. Does that seem reasonable? If I break this bond heterolytically, which means I don't tear the electron pair in half, I give the bonding electrons or previously bonding electrons to one atom or the other. Why do you think oxygen gets this electron pair rather than hydrogen? Because oxygen is more electronegative. Did you learn in Chemistry 2045 that it's a lot of fun to think about electronegativity? A lot of fun. Fluorine, oxygen, nitrogen. 3 top dogs. Right? Wonderful. Now, last point for this system. In making 1 molar HAC, you learned about this in 2045. To what extent does this reaction go relative to this reaction? Does it go to a large extent? Does it go completely? In 1 molar acetic acid, I will tell you that this reaction only goes 0.4%. That's all. And you can find that out by studies like conductivity. Do you remember doing studies like that? Do you remember assignment 4 in 2045 laboratory? Which I purposely designed to set foundation for this kind of stuff. In assignment 4, 2045 laboratory, you learn that acetic acid only reacts with water to a small extent by this ionization process. So, after this goes to its 0.4% extent, then this goes. So now we have finally an equilibrium system. So the last directive for today is, right now on your paper, write the equilibrium constant expression for this equilibrium system. K expression. How many wrote that? Because what we are having on the board is correct. Solvent is not contained, and all the other components of this equilibrium system are aqueous phase solute species. 2 derived from the solute, hydronium ion acetate ion, as well as water. And 1, the solute itself, acetic acid. We'll pick it up from this point on Monday.